Hello, my name is Jonathan Looney. I'm a software engineering manager at Netflix. I manage the team that develops and maintains the operating system that runs on our content caches that deliver streaming video to our 200 million members around the world. I'm very pleased to be able to talk with you today. I want to thank the conference organizers for inviting me to speak. They told me that you think of storage in the broadest possible sense. And I guess that in that sense, you can think of a CDN as a gigantic storage area network if you want to. It is a gigantic storage and retrieval system, which holds Netflix's video catalog and delivers that to our members around the world. I hope you find what I have to say today interesting and informative and perhaps even enjoyable. I'm going to begin by talking a little bit about Netflix's CDN, which we call Open Connect. And then I'll move on to talking about some of the specifics of the way that we view storage and the way we use it within our CDN. And finally, I'll talk about some of the operating system optimizations that we've done to make the OCAs operate as efficiently as possible. So let's begin by talking about Open Connect. Open Connect is Netflix's content delivery network. It is global, widely distributed, and purpose-built for distributing Netflix's content. We try to keep the CDN as generic as possible in order to reduce complexity and help us leverage standard tools. However, we do customize things where there's a benefit for us to do so. Netflix applications use both cloud computing and assets from our CDN. And so let's talk a bit about the way that the clients use the CDN. And I'll give you some context about the way that our CDN is used. At startup, the application gets data from the cloud computing system, but it also loads some static data from the CDN. The application then uses the cloud computing system to get a list of movies to show, but it loads the box art, that is, the graphics associated with the title, from the CDN. And finally, once you click play to start a video, the application gets information about the video's files from the cloud computing system. The cloud computing system will tell the application how to retrieve the video, audio, and subtitle files from the CDN. And at that point, the application will go and actually fetch the data from the CDN, fetch the video and the audio and the subtitles from the CDN, and begin displaying your video to you. So you can see the CDN is involved in many different aspects of the Netflix application's operation, but probably the part where we serve the most data is the videos that our clients actually watch. Open Connect delivers streaming video to over 200 million members, delivering over 100 terabits per second at peak. It's very humbling to work in this environment where the things that we do impact so many people. And the changes that we make can have such far-reaching impacts. Obviously, working at this large scale also makes the challenges harder, but it also makes the job rewarding because even small improvements can make a difference. The Open Connect appliance, or OCA, is the content cache which holds our data files and delivers them to the end users. The OCA is the workhorse of the Open Connect network, and it runs almost exclusively open source software, including its operating system, which is based on FreeBSD. As much as possible, we try to use commodity hardware rather than developing custom hardware for our content caches. We also try as much as possible to make them as cost efficient as possible, both to produce and to operate. The appliances are designed to operate mostly autonomously. They do interact with a control plane, and they tell the control plane what files are available on them and their availability to serve new connections. They also receive data from the control plane that helps them to know what they should do, including what files they should download. But they should continue to operate even if they temporarily lose contact with the control plane. They should continue to be able to serve data. We have designed them to be able to continue operating even with the failure of some components. And so, for example, if a hard drive fails, they can often keep operating in place just with a slightly reduced capacity. And they may be able to operate even with the failure of some other components, again, with a potential reduction in capacity. We also have designed the system to have enough redundancy so that we can lose appliances without impacting the overall system availability. And so this gives us a fairly, we hope that this failure model gives us a decent amount of flexibility in practice to deal with failures. This is the typical Netflix OCA workload. In some ways, this is not very complicated. You bring bits off the storage devices into memory, optionally encrypt them, and then send them out network ports. This is a very typical web server workload. Just about anyone should be able to build a system which does this at low to moderate performance. And given enough money, just about anyone should be able to build a system which does this with high performance. What we try to do is get increasing levels of performance at the same or lower cost as measured by dollars per gigabit served. This diagram helps to illustrate the contended resources in the system. We have disk capacity, we have, which has a certain performance. We have memory capacity with a certain performance. And we have network port limitations as well. And obviously the CPU has a certain number of cycles available. But in addition to those things, the connections between these also are resources. And so PCIe lanes are resources. And memory bandwidth is a resource that we need to track and keep and optimize. Likewise, even the I/O controllers and the memory controllers can become bottlenecks. And what we're trying to do is to efficiently use all of these resources. So any of these things can become bottlenecks. And if any of these things become overloaded, or if we run out of any of these resources, they can limit the capacity of the entire system. On the other hand, if we overbuy, if we buy too many of any of these resources, it can be an inefficient use of our money. And we can end up wasting extra capacity that's in these resources, which is not needed. A final aspect, which is not necessarily directly shown in this diagram, but a final aspect which we try to optimize is power usage. Obviously, that is somewhat related to the things that are shown in the diagram, because the larger the size of these items that we buy, or actually just buying the wrong size of any of these items, can end up leading to a power inefficiency as well. Using commodity parts, we achieve 180 gigabits per second, serving TLS encrypted connections, while using less than 50% CPU on a single 32-core, 2.5 gigahertz CPU in a 2 rack unit format. We're very excited about this. And in fact, we hope to be able to almost double that, or basically double that capacity using the same hardware within about the next year. So let's move on to talking about some details about the way that we use storage. All of our systems have some flash-based storage. We've been moving from SATA-attached SSDs to NVMe-attached SSDs. We use hard drives in systems that need to store a larger amount of data. We are moving to use dual actuators, and we're planning to do our first wide-scale deployment of dual actuator drives later this year. We have three different flavors of OCAs for different workloads. Our all-flash appliances have a narrow amount of popular files, but they serve them very efficiently. So they generally store less than the OCAs that have spinning disks in them. But the files that they serve very efficiently. For many years, we used 100 gigabits per second attached flash appliances, and we ran them at 90 gigabits per second. This year, we're deploying an appliance which supports 4 by 100 gigabit per second attachment. And initially, we're planning to serve 180 gigabits per second at launch. But we do believe we'll be able to double that, or basically double that in the near future. Appliances with spinning disks hold a larger amount of files, but they serve them slightly less efficiently. The spinning disk appliances also have some flash storage within them, and we try to balance the files appropriately between the spinning drives and the flash drives to get the performance that we hope to get out of the system. We also have two options of OCAs that have spinning disks in them. One has a larger amount of storage and operates at a higher bandwidth, currently up to 80 gigabits per second. But we're planning to increase that up to 180 gigabits per second for the larger spinning disk appliances, hopefully by the end of the year. Our smaller spinning disk appliance currently serves up to 7 gigabits per second. But again, we're hoping to increase that, and we're targeting 21 or more gigabits per second for that by the end of the year. Now, we don't necessarily need these highest performance options in all of our sites, and not all of our caches have the demand to produce this much throughput. However, the extra capacity helps us to reduce our footprint in sites which do need the high capacity, and it provides room for growth in other sites. For file systems, we currently use UFS everywhere. We currently use UFS for our content drives, and we plan to continue to do that for the indefinite future. And one of the big benefits for us of using UFS is that it allows us to do a zero-copy send file on FreeBSD, which is, again, the operating system that our caches are based on. We'll talk about why send file is important in a few minutes, but it is very important for us and for the performance we get out of these caches. And so we plan to continue to use UFS indefinitely for the content drives. For the non-content partitions, such as our root partitions, logging partition, etc., we currently use UFS, but we're testing a move to ZFS for these non-content partitions. And we probably will end up deploying that beginning in the next month or two, and then gradually expanding out to more and more of the fleet as we gain more confidence in that. Obviously, ZFS is a well-tested thing. So when I say we need to gain more confidence in that, it's not so much that we need to gain confidence in ZFS as much as we need to gain confidence in how it works in our systems, and in the way that we will manage that and use that within our appliances. It's probably helpful to have some context on the way that we view our data. Our data is disposable, which is to say that we have so many redundant copies spread through our CDN that we can tolerate drive failures without sacrificing our ability to serve content. This buys us some cost advantages because we can buy slightly cheaper storage components and tolerate the elevated failure rate we get from using those in our CDN. We also pre-position almost all of our content. In other words, we do fairly little on-demand caching. Almost everything is pre-positioned, and the control plane tells the OCAs which content they should download, and then they download that content and they report back to the control plane that it's available. The control plane then sends our appliances to get the data or to get these video files from the OCAs that are best positioned to serve it to them. So we pre-position almost all of our content on the OCAs. And in fact, that's part of the value proposition that we offer to our ISP partners who host OCAs in their network. They can have some control over when we'll download content onto those caches. And so they can control when that traffic will be going over their network. This pre-positioning is guided by algorithms to predict how many copies we'll need on each server. And in fact, content placement is incredibly important for our efficiency. We need the right number of copies on each file, so we can meet the demand from our customers for that content. Further, we need those copies to be close enough to our members so they can download the content with sufficient performance. Moreover, the content needs to be spread across the correct servers in each location to be able to meet the demands of the clients with appropriate efficiency. And we even need the content to be spread across the correct disks in each server so we can meet the demand efficiently. If we get any of these things wrong, we can end up with hotspots, which reduce performance or efficiency. And that can be by having too many people too many members trying to download the content from too few copies that are spread throughout the CDN, to having even just a single disk in a single OCA have too much load on it, which keeps it from being able to serve with the performance that we expect to get out of that disk. And so content placement is just incredibly important for us for efficiency purposes. The position on the disk even matters. A while ago, someone in the OCA development group realized that we could get better performance from the outside of the spinning disks than the inside of the spinning disks, because the outside of the spinning disks move faster than the inside of the spinning disks. And by positioning our most popular content on the outside of the disks, we're able to read that data off the disks faster. That also has the side effect of grouping our most popular content together, which should reduce the seek times by letting the head stay in the same general area more of the time. When we deployed this technique, I think we saw somewhere around a 15% throughput boost. We also try to be smart about disk I/O. We use read-ahead on spinning drives, not our flash drives, but the spinning drives, to give us fewer reads with larger read sizes. Plus, using read-ahead makes sure that that data gets into memory sooner. The theory is that the client that is asking to read a megabyte of a file will probably want to read the next little bit of the file very soon. And so by pre-reading that data into our memory, it gives us a head start on serving what we hope will be the next request from the client. We do this on spinning drives, but again, we don't do this on flash drives because it seems like the performance trade-off of doing the read-aheads makes sense with the spinning drives, but we didn't find that it made as much sense for us to do that with flash drives. We also keep more popular files in memory longer than less popular files. Keeping heavily accessed files in memory helps us to avoid additional I/O. We also are very careful about mixing reads and writes. if possible, it would be great if we could maintain a completely read-only or completely write-only environment. But we do mix low levels of writes with high levels of reads, or reduced levels of reads with higher levels of writes. But we do try to be careful about how we mix those together, because combining them together can lead to changes in performance. And it can be, in particular, you can find that the reads off of the disks, in the face of high levels of writes, you can find that the reads off the disks will not achieve the performance targets that we have for them. And you'll end up with some inconsistency in how fast we're able to read the data, leading to, again, the reads failing to meet the performance targets that we have for them. We also try to pace out disruptive operations like trims to avoid impact to our other I/O operations. We found that on some SSDs or some flash devices, when we bombard them with a very large number of trims, it can impact our ability to read or write to the drives and lead to unexpected I/O response times. And so we try to pace those out to avoid any high levels of impact to our other I/O operations. So let's talk a little bit about the OCA operating system optimizations. If I had to summarize what my group does, I would say that it's driving efficiencies into the system. Whether we're trying to get an additional 2 gigabits per second out of an OCA's NIC, or reduce power consumption, we are fundamentally trying to drive efficiencies into the system. When we can make our existing hardware serve more data, we can perhaps reduce the number of OCAs we buy. Furthermore, if we can make hardware serve more data with less resources, we can potentially buy fewer resources for newer OCAs. And when we can reduce power consumption, we can reduce the cost to run an OCA as well as conserve some natural resources. And so I would say, I'd summarize what my group does by driving efficiencies into the system. And I've grouped some major efficiency efforts into 4 high-level categories. We realized several years ago that we were running out of memory bandwidth, which was causing our CPUs to stall. Closely related to this is whether the data is hot in the CPU cache. We've used various techniques to reduce memory bandwidth usage and increase CPU cache hits. Because CPUs can stall while accessing memory, this makes a drastic difference in the perceived performance of our CPUs. Another broad area where we drive efficiency is using hardware offloads to reduce memory bandwidth and/or reduce CPU cycles. In our testing in our environment, it looks like this has the further impact, in some cases, of also being much more power efficient. Another broad area where we work on efficiency is using PCIe bandwidth and/or I/O controller resources efficiently. This can allow us to achieve increased throughput of data over the PCIe bus. Finally, a broad area where we work to drive efficiencies by enabling new platforms or designs which will allow us to deliver data more efficiently. So one of the mechanisms that we use is async send file, or asynchronous send file. I've chosen to group this under reducing memory bandwidth because it does reduce memory bandwidth. But async send file also helps to avoid context switches by keeping our data in the kernel. Async send file allows a user space application to request the kernel send bytes from a file with an optional header and trailer. The send file call will set up any necessary I/O requests and then immediately return to the user space caller, allowing the user space program to continue processing other connections. The I/O work then completes asynchronously, hence the asynchronous send file. Once any necessary I/O is completed, the kernel will queue the data for transmission in appropriate network buffers. This has several obvious benefits. It avoids copies between user space and kernel space. It also allows the user space application to avoid most blocking on I/O. But it has an additional benefit for unencrypted connections. Because the network buffer points back to the files buffer in the VM page cache in kernel memory, we can avoid an additional copy of the file's contents to the network buffer. One obvious limitation of send file is that it will only work for unencrypted connections. So a further optimization we use is deploying in-kernel software-based TLS encryption, which we call kernel TLS, or KTLS for short. We deploy this in combination with send file, which lets us retain almost all the benefits of asynchronous send file, while also being able to add TLS encryption. The one thing that we do lose in this is that it does require a per connection copy of the encrypted data. And so rather than having all the socket buffers point back to the unencrypted file data in the VM page cache, rather we need to encrypt the data with the TLS session key for a given session, and then store that encrypted data in the socket buffers. And so this adds a round trip over the memory bus. And it also requires the extra memory to store the encrypted data. However, this is still much more efficient than copying the data to user space, encrypting it, and then copying it back to the kernel network buffers. Several years ago, we realized that we were running out of memory bandwidth. This appeared as high CPU utilization, but we realized that the CPU was actually stalling while waiting for memory accesses to complete. So one of my team members went on a war against memory inefficiencies. One way he improved our memory bandwidth usage was reorganizing data structures to make them either use less cache lines or grouping highly used fields into fewer cache lines. This benefits us in at least 3 ways. First, it reduces the amount of memory bandwidth we use for these data structures. Second, it reduces the number of cache lines we use, which enables us to keep more memory in the cache. And third, it should also reduce the probability that cache line aliasing will impact any given data structure. You can see on the screen a somewhat contrived example of this. So imagine that this is a data structure which uses 3 cache lines. I've put several fields in here, highlighted in yellow, which are heavily used fields. And you can see that at the moment, they're spread over all 3 cache lines. If we instead simply reorganize the data structure, we can get the heavily used fields into a single cache line, which will allow the CPU to access that one cache line when it needs to use these heavily used fields, rather than having to access all 3. Another optimization he implemented was to coalesce data structures. In particular, he added an optimization to FreeBSD's network buffers, which are called MBuffs. Prior to his change, when you used send file to send data on a network connection, you would end up with a chain of MBuffs, which each pointed to a single memory page. He implemented an optimization which allowed the MBuffs to store a collection of pages in an array in a single MBuff. This drastically reduced the number of MBuffs used in the system, but it also made it so that the kernel had to touch many less MBuffs to send the same amount of data. And it turns out that it's actually rather expensive to walk a chain of MBuffs, each of which points to a single memory page. And by contrast, having a single MBuff, which points to an array of memory pages, performs much better and results in reduced memory usage and reduced memory bandwidth usage as well. And so Using this technique, the kernel has to touch less memory when it's transmitting the same amount of data. We also we also use some optimizations related to TCP. The TCP input path is a big user of both memory bandwidth and CPU cycles. It turns out that it's actually rather expensive to find a matching TCP connection out of tens of thousands of connections, load all the state for that connection, process an input packet, which will change that state, and then process the necessary follow-up actions, such as sending the packet to the peer or waking up user space processes. Large receive offload, or LRO, helps with this by coalescing packets for the same connection. And if you look on the left side of the slide, you'll see an example where we have 5 packets that we've received for 3 different connections. Hans-Petter Selaski added an optimization to FreeBSD's LRO algorithm several years ago. So this is something that someone outside of our organization contributed to upstream FreeBSD, but which has been very helpful to us. So Hans-Petter added this optimization to use a packet's RSS information to efficiently sort the incoming packets. And you'll see in the center of the screen that those packets from the left side have now been sorted into a given connection. And so the packets now are grouped together with the packets from the same connection being adjacent to each other. This makes it much more likely that the packets from a given connection will be adjacent and therefore will be coalesced, which is what you should see on the right side of the screen. And so using this technique makes the LRO aggregation much more efficient and allows us to see much better gains from this feature. And so using this feature, you see that you start off with a collection of packets on the left, which get sorted by connection in the middle. And then on the right side of the screen, they end up being coalesced into just a single packet, hopefully, which can be processed all at once by the TCP input path. Again, this saves us a decent amount of both memory bandwidth and CPU cycles. We've also benefited from some optimizations which others have added to the virtual memory system in upstream FreeBSD. For example, the per CPU page caches greatly reduce the cost to allocate in free memory pages by keeping a CPU local cache of free pages. Because the cache is CPU local, there should be little or no contention for the locks and little or no contention for the CPU cache lines which hold the page cache. When the kernel needs to allocate a page, you can try to allocate it from the local cache before going back to the shared memory allocator pools. Batched frees further reduce the cost of freed memory by keeping a CPU local cache of pages, which need to be freed back to the shared memory allocator pools. The CPU can then periodically free those back to the shared pools, only acquiring the locks one time to do multiple frees. Moving on to hardware offloads, there are several hardware offloads which we either currently use or are experimenting with deploying in production. The first of those is TCP segmentation offload, or TSO. Using TSO, we can have the TCP stack send a large data packet, which the NIC will segment into MSS-sized chunks. This is much more efficient than having the TCP stack run through the TCP output routine once for each MSS-sized packet, and then send the MSS-sized packet down the stack through the IP and Ethernet output routines. This optimization produces very substantial improvements for us. In an experiment from several years ago, we found that one of our 100 gigabit per second attached caches could serve about 26% less bandwidth when we disabled TSO. And so it's a real performance win for us to be able to send large packets through the kernel and then have the NIC do the segmentation for us. Another offload, which we are close to deploying in production, is inline TLS encryption. When this feature is activated, the kernel programs the NIC with the TLS session's encryption key. The kernel then sends plain text data to the NIC, which encrypts it before transmitting it. Because we want to control many facets of the TCP session, we're not using a full TCP offload engine implementation. Rather, the NIC is simply encrypting packets for us before transmitting them. A benefit of this is because the data remains unencrypted in the kernel, we can go back to using having the socket buffers point to the file contents in the VM page cache. And so we get to avoid the memory round trip of copying that data to a given connection socket buffers. And we get to save the memory from having that extra copy. We're very close to deploying this in production. With inline TLS encryption, we're able to save a significant amount of memory bandwidth and CPU cycles, and we're able to achieve lower power consumption per bit served. In addition to memory bandwidth, another resource which we need to utilize carefully is PCIe bandwidth. When the pandemic-related shutdowns began, we really didn't know what to expect for demand on our system. A number of people began looking for low-hanging fruit, which would increase the efficiency of our systems. Now, for the most part, we avoided rushing unneeded optimizations into production. But one optimization which did get quickly implemented made a lot of sense. Someone on my team noticed that we were DMAing at least 3 memory segments for each TLS record: the header, the 4 kilobyte, or the data, so at least one 4 kilobyte page of data, and then the trailer. This is an artifact of the way that these are stored in the network buffers that we use for kernel TLS. He added an optimization to try to coalesce the header and the trailer into adjacent memory segments, which eliminated the need for an extra DMA read for many packets. That allowed us to move from a maximum bandwidth of 90 gigabits per second to 92 gigabits per second on a number of 100 gigabit per second attached flash caches. An example of the work we've done to enable new platforms or new designs is the work we've done on NUMA. To this day, all of our OCAs have been single socket appliances, and our future plans remain single socket. However, even single socket CPUs can now require NUMA in order to achieve maximum performance. Over the past several years, we've either sponsored or co-sponsored some work to improve FreeBSD's NUMA support. But we've also done internal development work to figure out how to take advantage of NUMA in a way that adds efficiency. This work has led us to the point where we can now efficiently take advantage of single socket CPUs which use NUMA domains internally. And we're also at the point where we can evaluate multi-socket systems. Even though we currently don't have plans to deploy a multi-socket system, it's nice to have the flexibility to evaluate them if that makes sense. So obviously the big question when you're talking about NUMA is how are you going to manage your data flow? Where's your data going to live? And what are you going to allow to cross between NUMA domains? So our team did some experiments, and we decided that we were going to go with NIC locality, if you will. And so when a session first arrives on a NIC, we pin it to that NUMA domain, whatever NUMA domain that NIC is on. And then we try to keep all the state associated with that session local. So we'll keep the TCP session state in the RAM in that NUMA domain, and we'll pin it to a web server process running on the CPU in that NUMA domain. And we'll try to keep all the state local. The one thing that may need to cross between NUMA domains is the actual contents of the file that the user wants to read. Until they've actually made their request, we don't know which file they want to read. And in fact, they might want to read multiple files, which could be in different NUMA domains. rather than migrating the connection between NUMA domains, we made the decision to keep everything local on the NUMA domain, but allow the bulk storage transfer to cross over between the NUMA on the connections between the NUMA domains. And so when they request something that lives on a storage device attached to a different NUMA domain, we allow that one DMA to transfer the data from the storage device to the RAM, which lives in the NUMA domain where the connection arrived. Other than that, we'd like all the data to stay local. And we decided that that seemed to give us the best performance for our workload. So in summary, I'm going to come back to this slide, which shows the typical Netflix OCA workload. You'll see that I've modified it to show the possibility of inline TLS offload to the NIC. But other than that, it's fundamentally the same slide I showed earlier, which gives our workload. And again, the workload is fairly simple. We take bits from the disk, we put them into memory, we optionally encrypt them, and then we send them out to the network ports. But this is where we end up spending the bulk of, I think this is where we end up spending the bulk of our engineering time. And so I think it's a good summary of what my team does and what the hardware team does as well. We're trying to make the OCA work well as a system. And so that means that we need the right amount of each of the resources that are shown here. We need the right amount of capacity, the right amount of interconnections. We need the right amount of resources. We don't want any of the resources to be a bottleneck, which keeps the other ones from being fully utilized. And on the flip side, we also don't want to needlessly overbuy or over provision these resources either in ways that will be wasteful. And so we need to make sure we have a big enough CPU, we have enough memory bandwidth, we have enough PCIe lanes, we have enough capacity on the storage devices, we have enough capacity in the RAM, and we have enough network ports. And we want to make sure that these are all correctly sized. And so, again, I think that fundamentally a lot of what we're doing, while we're doing very detailed work to make sure that we're using these resources efficiently, and sometimes what we're doing is really gets down into the weeds of the way these things work or the way the system works. Fundamentally, what we're trying to do, though, is meet the systems engineering goal of having a well-designed, efficient system which works together well and produces increasing value for us by having good efficiency. And our experience has been that we can see great efficiency gains by paying attention to each of these components, including the connections between them, and writing our software to optimize the way we use these resources, and designing our hardware to have the right amount of each of these resources. So I want to thank you for allowing me to speak to you today. I want to thank you for coming to the talk. I hope that you have found it informative and educational and, again, perhaps even enjoyable. And again, I also want to thank the conference organizers for inviting me to speak. And I hope that you found this presentation useful. And I believe there will now be an opportunity for questions if there are any.